Hello everybody, we have a problem here in basic quantum mechanics to solve. In this problem it is stated that the wave function for identical fermions is anti-symmetric under particle interchange. Which of the following is a consequence of this property? A. Pauli exclusion principle. B. Bohr correspondence principle. C. Heisenberg uncertainty principle. D. Bose-Einstein condensation. And E. Fermi's golden rule. The correct answer is A, the Pauli exclusion principle, and I explain the reason now. According to the Pauli exclusion principle, no two identical fermions occupy the same space at the same time, or in other words, they can't be at the same point in space simultaneously unless they have opposite spins. That is, they exclude each other if they get the same spins. And this follows only if the overall wave function, that is the spin part of the wave function times the space part of the wave function, is anti-symmetric under the interchange of the two fermions. Let us write the overall wave function of two fermions, two identical fermions. Let it be phi for particle 1 and 2. This wave function has got two parts in it. One is the spin part of the wave function. Let us denote that by S for particle 1 and 2, and the other is the space part of the wave function. Let us denote it by psi for particle 1 and 2. Now the overall wave function phi is anti-symmetric. Now there are two possibilities in it here. Either the spin wave function is symmetric, denoted by S, small s, and the corresponding space part of the wave function should be anti-symmetric then. Or take the spin part of the wave function as anti-symmetric, then in that case the space part of the wave function should be symmetric in order to make the entire wave function as anti-symmetric. Now let us assume we have two identical fermions that have the same spins. In this case, the corresponding spin wave function should be symmetric under the interchange of the two fermions. Of course, I am avoiding some details about the spin wave function of the two fermion system here, but hopefully you will be able to understand it at the end of the video. But now, the space wave function should be anti-symmetric under the interchange, and this will ensure that no two fermions with the same spins can exist at the same point in space. So let us write the anti-symmetric space wave function. For this purpose, let us assume we have two fermions, say fermion 1, described by a wave function psi1 with a position variable x1, say, and there is another identical fermion here which is described by a wave function psi2 with a position variable x2. Now the combined wave function of space wave function of these two fermions can be written as psi1 since they are independent, so psi1 times x1 as function of x1 multiplied by psi2 as function of x2. But now, since these two fermions are not even identical, they are indistinguishable also. You cannot distinguish between the two if you switch their position. So I should also write that possibility here, that psi1 particle 1 at position x2, say, and multiplied by psi2 at position x1. These states are equally probable, so I should write in front of it a factor of 1 by 2 under the root. But about the sign here, if I put the sign here as negative, this state will be anti-symmetric under the interchange of two particles. But if I put a positive sign here, the state will be symmetric under the interchange of the two particles. But I need here a state which is anti-symmetric under the interchange of two particles. So write it down here. Psi anti-symmetric of particle 1 and 2 is equal to this. Now you might wonder, what does an anti-symmetric wave function means? It means that if you switch the position of the two fermions, what happens? The wave function changes sign from positive to negative or from negative to positive. Let us see that here. So psi anti-symmetric of particle 1 and 2. I write here this symbol. I switch the positions of particle 1 and 2. What happens to the wave function now? It is equal to 1 by 2 under the root psi 1 now at x2. I'm switching the positions, and multiplied by psi 1 at x1, psi 2 at x1 minus psi 1 at x1 multiplied by psi 2 at x2. Now see here, this is equal to minus 1 by 2 under the root psi 1 at x1 multiplied by psi 2 at x2 and minus sign psi 1 at x2 and psi 2 at x1, and this. Now this is equal to minus psi anti-symmetric, this wave function actually, this one. So psi anti-symmetric 1 and 2. So this is the property of an anti-symmetric wave function, that it changes sign under the interchange of two particles. Now let us see what happens to our anti-symmetric space part of the wave function when our two identical fermions which have the same spins are put at the same point in space. So psi anti-symmetric 1 and 2. Same point means x1 is equal to x2 is equal to x. So let us write our wave function for this case. Psi 1 at x multiplied by psi 2 here at x minus psi 1 at x and multiplied by psi 2 at x. And we see this wave function is 0. It is equal to 0, which means that having two fermions with the same spin at the same point in space is impossible. And this is actually the Pauli exclusion principle. Now, on the other hand, if we have two identical fermions in opposite spin states, the spin wave function will in this case be anti-symmetric, and therefore the space part will be symmetric in order to make the overall wave function anti-symmetric. Now, in the symmetric space wave function, you can put the two fermions at the same place without making the space wave function vanish. But remember now that the spins are opposite, and we can do so according to the Pauli exclusion principle. Thanks for watching, guys.